Good morning, everyone. My name is Hirokjyoti Hazarika, and I'm a student of Mechanical Engineering Department 6M. And today, I'm going to solve in MATLAB code for the two-dimensional steady-state heat conduction equation using finite volume method, where we have to use non-uniform grid spacing with different del x and del y and boundary conditions with left and right temperature fixed, which is a Dirichlet condition, and top and bottom are insulated plate, which is Newman conditions. Our problem is divided into 5 parts. First is the problem parameters. We have taken our length in terms of meter, which is 1 in the x direction, and in the y direction, it is it is taken as 1 meter in the y direction. The temperature at the left is taken as 100 degrees centigrade, where we have a fixed temperature along the boundary. And right in the right side of the grid, we have taken our temperature at 40 degrees centigrade, and the thermal conductivity is at the rate of 1 watt per meter Kelvin. And our next part is the grid generation, where we are asked to take non-uniform grid spacing. So our total grid points in the x direction is 20, and the total grid points in the y direction is 20. So we have a total grid points of 400, 20 by 20. So the next is to generate non-uniform grid in the x direction. Here we have taken the initial values to be 0 for each grid, and the coordinates start from at nx plus 1 at 1. So basically we are leaving the face grid points in their exact location, and then we are moving on to the next grid point for our calculation, and their initial values are at 0. We are using the for loop for this difference in the spacing, which is at x of I of their particular element, which we will add 0.002 increment plus with 0.002 multiplied by I minus 1. This is the way we are increasing the spacing of our grid points. And we are doing the same condition for in the y direction also, with the same amount of increment except for this part where we have taken a 0.0015 into j minus 1. And our next is calculation of the grid spacing, which is by using the difference in their nodes. And the next is the interpolation method, where we have taken as the x a1 and in1 with addition of their difference in the two locations. Here we will move on to the next part, which is our initialization of the temperature field. Here we have taken our initialization or starting temperatures of each grid points at 0 degrees centigrade in all the directions. The next is our boundary conditions. Here we have taken our left boundary at fixed temperature of 100 degrees centigrade, where we have taken our value as here, and our right side is taken at 40 degrees centigrade of fixed temperature, which is the value of here. And the top and bottom boundaries are insulated, which is basically Newman condition. That that means our difference of temperature with respect to y is 0, and our fluxes are also set to 0. The next is our solution. Here we have taken our maximum iterations to be up to 10,000, and our tolerance in our difference of our temperatures is up to 1 into 10 to the power minus 6, and with our iteration starting from at 0. Here we replace our T old temperature with T new after each iteration if our condition of tolerance of 1 into 10 to the power minus 6 is not fulfilled. We start from our for while loop, which is at 2 into x and x minus 1, starting from our grid point next after the phase. The next point of right after the phase, when we are excluding the phase grid points. So we have taken it in our direction of to with west, east, south, and north directions. For west, we have taken as x into y I minus x into I minus j with interpolation of the differences. Similarly, for e, we have taken as for plus one direction in our east direction, which is at x into x minus 1 plus I minus xi. The south direction, which is the similar to as west, but replaced by j. And for north, also similar to east, but replaced by j. Phase conductances. Where here we calculate the k value of our in each direction. For west, it is direction into of our difference of in the west direction by addition of difference in their coordinates. Similarly for east, south, and north. Next is the coefficients of the in each directions of their respective grid points. For west, it is at dyg. And we update our temperature by having this our formula in AW into T J into J minus 1 for each coordinate divided by APF, which is basically the average of their full coefficients. That way we get the updated temperature of each grid point. And next is we take the difference of their absolute difference and we see when it is our when we have our maximum difference from the new temperature to the previous temperature, which is at T old. The temperature is greater than to our tolerance, which is at our 10 to the power minus 6. Then we move on, we put it in the T old value, which is basically T value as T old, and then we do another iteration of again. In that way, we are calculating unless and until the difference is below 10 to the power minus 6. After the FVM solution, we move on to the next, which is our post-processing. Here we are going to show our solution in terms of heat map in color map as well as with graph. So first we need to create the grid points for plotting, which is basically our x into y, x and y, our mesh grid, which is the x points and y points, and our x in x direction our grid points were 20 and our y direction were 20, basically of 400 grid points. Then we plot our temperature control, where we have taken our temperature x, y, and t at 20 grid points at in line using the line color below. And we have taken our title as two-dimensional steady-state temperature distribution. X in x direction we have taken as x meter and y direction y meter. And our color map is at jet. Plot temperature profile along center line. So we will plot the temperature profile, how the along the center line, how the temperature is varying with time for the because of the difference in temperature at the in the left side and as well as the temperature at the right side. So here we plot our T round and we have a 2. Our line width is at 2, means our differential values are 2. Title will be a temperature profile along center line is equals to y equal difference of y divided by 2. Then our grid points is 1. So now we calculate run and see our graph. This is the variation. This is the temperature distribution of our results, and this is the graph of our temperature profile along the center line. Along the center line with push points. And here we can see our temperature is increasing from the left side as well as and it is decreasing towards the center line. And at our left side, it is our temperature 40 degrees centigrade. So some part of heat is also flowing towards the center portion. That way we can see that our with the direction from left to right, the temperature is slowly decreasing from 100 to zero point 0.6. At around this point, our temperature is again increasing up to 40 degrees centigrade. In this way, we are able to plot how the temperature difference will be for two-dimensional steady-state heat conduction equation using the FVM method with non-uniform grid spacing